decided by an administrator. It should be decided by scientists working on the data from 3i Atlas.
Most comets behave like slow, blurry clouds drifting through space, but the latest images of interstellar visitor 3i Atlas just revealed something no one expected. Instead of a wide, hazy tail, astronomers found a razor-thin jet stretching out from the nucleus like a perfectly drawn line. This structure stays straight, even at extreme zoom, and it refuses to spread, bend, or drift the way comet dust normally does. Let's break down what these new images show, why this jet is so unusually focused, and what it might mean for how comets from other star systems are built. And if the early data is right, then the biggest mystery may not be what the jet looks like, but how a frozen rock from another star can produce something this organized. The strangest comet pictures we've ever seen. The story really begins with a set of comet photos from Hawaii that were supposed to look normal, but didn't. Astronomers expected to see a fuzzy cloud around the comet, maybe a wide, soft tail drifting away. Nothing out of the ordinary. Instead, when the new images came in, the anti-tail looked sharp and unusually thin, almost like someone had sliced a line across the sky with a knife. Even before any special processing, it stood out as much more defined than earlier shots from the same month. When the astronomers zoomed in about 10 times, they thought the feature would blur or spread out the way comet dust normally does, but that never happened. The jet stayed tight and crisp, which instantly raised questions about what they were actually looking at. This is strange because in almost every example of a normal comet, dust behaves in a very simple way. When dust breaks off the comet's surface, each grain has a slightly different size and speed, and sunlight pushes on them all differently. It's like watching smoke rise from a fire, no matter how it starts. It spreads out into a wide shape, but in that first Hawaii zoom on 3IATLAS, the jet does the opposite. It doesn't spread into a fan. It doesn't fade into a soft blur. It holds a razor-thin line, which tells us the material isn't floating away randomly. It looks like it's being guided along a very specific direction. A few days later, another observer, Michael Georgia, captured an image on November the 28th that made the mystery even stronger. His equipment was nothing special, and his exposure times were short, but his photo shows an anti-tail so thin it almost looks drawn. There is no fuzz around it, no drift to the sides, and no sign of widening farther from the nucleus. That's unusual, because most tails spread out the longer they travel. Instead, his frame shows something straight, clean, and very geometric, which isn't what you'd expect from loose, drifting dust. Since any single photo could be a fluke, the Hawaii team went back to their own data to double-check. They processed the images to isolate the inner jet structure and remove some of the glow around it. What they found in that zoomed and cleaned-up frame was even stranger. The inner jet is unbelievably narrow, running across the image like a thread. Even as it moves away from the nucleus, it doesn't open up or curve. Normally, sunlight would push dust sideways and cause a broad cone-shaped plume, but here the line stays straight and smooth. It looks more like a focused spray coming from one fixed point on the comet's surface than the random venting we usually see. To see if the effect appeared in other observations, you can look at a pair of images processed by Calopa stars. In the left frame, which shows the inner coma, everything looks calm and undisturbed. There are no signs of the comet breaking apart, like extra bright spots or clumps. It's just a single, dense region around the nucleus. In the right frame, where they sharpened the jet structure, the anti-tail shoots out as a straight, thin beam that stays intact even after a heavy 10 times zoom. If the comet were releasing dust in a chaotic way, these processing steps would normally reveal a messy, uneven pattern. Instead, the structure holds firm, which suggests the source driving the jet is surprisingly stable. Another clue comes from looking at how the jet behaved over several nights. Observers took long exposure images on November 22nd, November 23rd, November 25th, and November 26th, and each night added its own details. The November 22nd image, a 23-minute stack, has a few cloudy edges, but even with that, the central jet stands straight and doesn't bend or twist. On November 23rd, the sky was clearer and the exposure was longer, so the central column became even more defined, though the axis stayed in the exact same position. On November 25th, with 31 minutes of exposure, you start to see faint ripples in the tail, which is normal for moving dust, but the main axis still doesn't shift. Then, on November 26th, the brightness of the coma increases and the halo around it expands, yet the core jet still doesn't deform at all. When the 4 nights of Hawaii images are placed side by side, the pattern is hard to ignore. Even though each night had different brightness, clarity, and noise, the jet's central line appears in the exact same orientation every time. Normal dust clouds drift, wobble, and change shape as a comet rotates, but this jet stays steady, almost like it's fixed to the nucleus. When dust and gas both point the same way, it's hard to call it an illusion. So what kind of hidden mechanism inside 3I Atlas could shape something this precise, and how much stranger might it get as we keep watching? How comets are supposed to behave, and why this one doesn't. To understand why 3I Atlas looks so strange, it helps to go back to the basics of what a comet actually is and how it normally behaves, because everything we're seeing in the Hawaii images goes against those expectations. A comet is basically a frozen mix of ice, dust, and rock. As it gets closer to the sun, the sunlight heats it up. The ice begins to turn straight into gas, a process called sublimation, and that gas carries dust with it. This creates the coma, which is the glowing cloud around the nucleus, and from there the dust gets pushed away by sunlight to form the dust tail. At the same time, the charged particles from the sun grab onto ionized gas and pull it in a different direction, forming the ion tail. These tails almost always look soft, wide, and a little messy because everything spreads out once it leaves the nucleus. If you imagine blowing on a handful of flour or watching smoke rise from a fire, you can picture how most comet dust behaves. The grains are different sizes, so they move differently, and sunlight pushes on them with different strengths. They drift, spread, and keep spreading the farther they travel. That's why comet tails usually look like big, fuzzy fans rather than sharp lines. Even if a comet produces a narrow jet at the beginning, the particles don't stay bunched tightly together for long. Even antitails, the features that seem to point toward the sun instead of away from it, don't behave the way 3I Atlas's antitail does. Antitails are usually an optical illusion caused by the angle from which we view a sheet of dust lying in the comet's orbital plane. Because of that, they appear wide and diffuse, and their shape shifts as Earth moves relative to the comet. They're not normally thin, rigid lines. So the extremely narrow antitail we see in the Hawaii images of 3I Atlas is already unusual before we even talk about anything else. Another important part of comet behavior comes from jets. Jets are narrow streams of gas and dust that shoot out from certain spots on the comet's surface when sunlight heats those areas more strongly. At first, a jet can look thin, but as it moves outward, the dust begins to spread out because it's not all identical. A rotating comet makes this even more complicated because as the nucleus spins, the jets shift direction, curve around, or create spiral-like shapes in long exposures. Over time, even a jet that starts narrow becomes wider and softer, and it rarely stays straight for long. This is why the inner coma image from Hawaii is so interesting. If 3I Atlas were breaking apart or shedding pieces, the coma would look uneven. There would be extra bright spots called secondary peaks, or little clumps of material that show the comet is splitting, but none of that appears in the frame. The inner region looks dense and smooth with one clear center. Nothing points to fragmentation. This matters because fragmentation is one of the only ways you might get unusually sharp structures, yet the comet doesn't show any of the signs that normally come with a breakup. Rotation is another important clue. Most comets spin, and when they do, the jets shift as the surface turns. That usually means the direction of the jet changes a little bit each night. It might lean slightly or wobble or twist depending on how the comet is rotating and how active its vents are. But in the multi-night Hawaii stack, November the 22, 23, 25, and 26, the jet doesn't do any of that. Even though the brightness and the outer halo change from night to night, the central line stays in the exact same place. It doesn't drift, bend, or curl. That's not normal for a comet that's releasing dust. Now, you might wonder whether the thin shape could be caused by the way the images were processed. After all, astronomers use stacking, sharpening, and zooming techniques that can sometimes make lines look sharper than they really are. But here's the thing. If the jet were chaotic, those same techniques would reveal the chaos. Stacking images from different nights would show little shifts or distortions. Sharpening would bring out noise or irregular patterns. Heavy zooming would magnify any wobbling. Instead, the shape stays stable through all the processing and across all the observers. That strongly suggests the jet's shape is really there. Here's something to think about. If comets are usually messy, why does this one look so organized? The truth is that none of the normal explanations, dust motion, anti-tail geometry, jet behavior, rotation, or fragmentation, fit what the images show. Everything we know about how comet dust behaves says that 3I Atlas should look wider, more uneven, and far less stable. Yet every frame, whether it's the first Hawaii shot, the zoomed data, or the multi-night collage, shows a structure that is narrow, steady, and very well formed. So, if 3I Atlas doesn't follow the usual rules of comets in our solar system, then what is actually happening inside this object? An interstellar visitor. When you look at all the photos of 3I Atlas together, from the first Hawaii close-ups, to the Michael Joerger frame, to the Calopa stars zoom, and the 4-night collage, you start to notice something that is hard to argue away. Every observer, using different equipment, on different nights, under different sky conditions, ends up capturing the exact same thin, straight core running out from the nucleus. It does not matter whether the image comes from a short exposure, a long exposure, a deep zoom, or a cleaned-up, processed frame, because the main jet shows up with the same steady structure every single time. That kind of agreement across independent observers is rare, and it forces you to step back and ask why so many different views are lining up in the same direction. One of the clearest examples of this is the Calopa stars collage, which puts 4 nights of Hawaii observations side by side. In that collage, you can see the halo around the jet change shape from night to night as the atmosphere shifts, because some evenings were clearer than others, and longer exposures brought out more of the background glow. The micro-textures in the outflow also change a little, showing tiny waves or ripples in the dust, which is completely normal. But the central axis of the jet refuses to budge. It does not tilt, it does not lean, it does not curve. Even though the overall brightness and outer halo grow and shrink depending on exposure length, the spine of the jet stays anchored in the same direction. When you realize that these frames were taken on November the 22, November the 23, November the 25, and November the 26, all with different levels of sky transparency, it becomes even more surprising that the underlying geometry stays untouched. Now, how do we know this thin line is not just a strange way the dust looks in visible light? The answer comes from data that does not rely on light at all. ALMA, the Atacama Large Millimeter and Submillimeter Array, made radio maps of molecules coming off the comet, especially methanol and hydrogen cyanide. These molecules give off radio waves that can be mapped like heat signatures, so astronomers can see exactly where the gas is coming from. In these maps, the emission is not spread out randomly around the comet. Instead, it is concentrated in one compact region, and the shape is slightly stretched in the exact same direction as the thin optical jet seen in the Hawaii photos. When two completely different kinds of observations, visible light and radio waves, line up this perfectly, it becomes much harder to argue that the narrow jet is an illusion. It means the jet is not only visible in the dust, it is written into the chemistry of the comet itself. Once you see that the evidence matches across light and chemistry, the next question becomes whether this behavior can be explained by normal comet physics. Astronomers have already suggested a few ideas that might explain the well-aligned structure. One possibility is a spin-locked vent, which means a crack or opening on the comet's surface always points in the same direction as the comet rotates. If the comet's rotation matches the direction of the jet, the outflow might stay steady instead of wobbling. Another idea is that there could be a narrow crack that channels gas in a very focused way, like water being forced through a nozzle. A third idea involves unusual layering of ices inside the nucleus. If certain ices vaporize more quickly than others, and they sit beneath a harder crust, the pressure might build and escape through a very small opening, which could naturally produce a thin jet. These ideas are helpful, but they run into the same problem once you look closely. Even a spin-locked vent would normally produce some drift or curvature over time, because the comet's rotation is never perfectly smooth. A narrow crack might produce a thin jet at the source, but dust still spreads as it moves outward. And yet the 3I Atlas jet stays tight even far from the nucleus. Unusual ice layering could make the jet strong and focused, but it doesn't fully explain why the line stays straight across so many nights and survives magnification and processing without breaking apart. In simple terms, these explanations get us part of the way there, but the jet's extreme thinness and long-range stability still strain the normal models. At this point, the shape of the jet almost looks guided, so it's natural that some people jump straight to the science fiction thought. Could this be some kind of alien technology? Before going any further, it's important to address that idea clearly and responsibly. Even though the jet looks unusually focused, there is no evidence of anything artificial here. There are no strange light curves suggesting signal patterns, no repeating pulses in radio data, and no glints or reflections that would hint at metal or machinery. The coma does not show any debris that looks like broken hardware, and the ALMA data does not reveal anything besides natural molecules like methanol and hydrogen cyanide. Everything we've seen so far fits the idea of a natural comet, even if the jet itself looks far more organized than what we're used to. So, if this is not artificial, why is an interstellar comet producing the kind of focused jet we usually only see from much larger and more energetic objects like black holes or young stars? Those systems produce narrow jets because they have enormous magnetic fields, fast rotation, and intense gravity shaping their outflows. A frozen chunk of ice and rock drifting through space shouldn't be able to mimic that kind of order, yet here we are looking at a jet that stays thin, straight, and steady over several nights. This leads to a more thoughtful and more scientific question. What is it about 3I Atlas, its structure, its materials, or the environment it came from that allows it to behave this way? Because even if everything about the jet is natural, it still suggests that interstellar comets might be built differently from the ones we see in our own solar system. Maybe the internal structure is layered in a way we don't see at home. Or maybe the comet formed in a region with a different temperature profile, pressure, or magnetic influence that shaped its vents and outgassing patterns more tightly. So, if a frozen object from another star system can produce something this precise, what does that say about the physics at work in the worlds it came from? And how many more surprises are waiting in the next interstellar visitor that crosses our sky? Thanks for watching. If you enjoyed this, don't forget to like, comment, and subscribe. Click the next video for more exciting content.